we've been talking about energy. We kind of went back to chapter 7. We talked about a couple of things, I think, last time. We talked about the idea, obviously, of the law of conservation of energy. We also saw some energy diagrams, I believe, as well. So two really big themes in terms of energy, right, is exothermic, which means heat and energy is released, and endothermic, which means basically that heat and energy is absorbed. And there's really sort of two ways that we sort of look at heat and energy in reactions. The first major way is delta H, which is the enthalpy. And if it is a exothermic reaction, the delta H and pretty much all energy sort of values will be a negative value. If it is a endothermic process, the delta H and pretty much all energy values will end up being a positive number. One way that we can calculate the enthalpy of a reaction is basically to take the delta H of the reaction is equal to the delta H of our products minus the delta H of our reactants. They are state functions, which basically means in most cases, the only thing we're interested in is basically where we start and where we end. So in a chemical reaction, where we end is obviously our products, and our reactants are obviously where we begin. I think we also looked at some energy diagrams, if I'm not mistaken, and if this is sort of an energy diagram here, our reactants are higher in energy than our products, and that is a exothermic reaction. Whenever you have that situation, basically for those reactants to get down to the products, it has to give off that energy. We also talked about the hill that everybody's got to climb, right, to get to the other side, and that is what is known as the activation energy. And to basically figure out the delta H for this reaction, like I said, we take the difference in the energy of our reactants to our products. And really that difference in energy is our delta H in a particular reaction. And in this case, it's obviously going to be a negative number. And that is simply if you just take delta H of the reaction is our products, delta H of our products minus the delta H of our reactants. Clearly our products is a lower number, right, than our reactants, which is a higher number. So if you take a lower number minus a higher number, you're going to end up with a negative number because the second number is larger. And that again is why our delta H would be negative. We also saw, I think, an energy diagram for an endothermic reaction, and that is sort of opposite. Our reactants are actually lower in energy than our products. And that would mean an endothermic reaction, again, to sort of get up there to the product side. Energy has to be put in, which again, endothermic is what that would mean. This again would be our activation energy, that hill. As we also talked about, the very top of the hill, that is the transition state. That is where you have what is referred to as the transition state complex. You have something that has basically bonds that have been broken or being broken as it comes through there, and also some bonds that are being made at the same time. So you have this sort of transition state complex at the very top, actually on both of these. And since that is sort of the peak of energy, things in high energy are not very stable, so they don't hang around a really long time. So they do fall down kind of to the other side relatively quickly. To calculate the delta H for this reaction, it is, again, the difference between the reactants energy and the products energy would be our delta H for this reaction. And it would end up being a positive number for kind of the same reason, or delta H of our reaction. Our products, which is a larger number or higher number, minus a lower number, which is our reactants. Again, higher number minus a lower number, again, to give you a positive number, or a larger number minus a smaller number, however you want to look at it. That will give you a positive value for delta H. Obviously, the activation energy affects the rate of a reaction. The bigger the hill everybody's got to climb to get to the other side, the longer it's going to take, right? And not all collisions result in products being formed. You do have to have collisions in the right orientation with the right amount of energy to get up and over to the other side. Again, I think we might have also talked about a catalyst in terms of energy here. And a catalyst, again, finds an alternative pathway for the reaction to take place. Ultimately, what a catalyst will do, if this green line is the catalyst reaction, it will lower the activation energy. So a catalyst will lower the activation energy. Thus, by lowering the activation energy, that's going to allow a greater proportion of molecules to get to the other side quicker, and thus the reaction will basically occur a lot faster. We also talked about that you can, if you have a reaction and a delta H value, and if you needed to do something like manipulate the equation, you needed to, for example, multiply everybody by 2. Maybe you needed 2 of everybody. The delta H value would then also get multiplied by 2. Also, if you needed to go back across and maybe you needed to divide by a common number. So let's just say here, in this case, you needed to divide by 2. Got to go through and divide by 2. You would divide your delta H value also by 2. So it's a little bit different in terms of manipulating the equations than what we see with equilibrium constants. Here, basically, you do the same thing to the value of delta H that you do to the equation. The other common thing is if you need to reverse a reaction, the delta H value changes sign. So it changes sign. So if I were to write the reverse of this reaction, it would still be 100, but it would be negative 100 if I was writing, 2D plus 2C, go to 2A plus 2B. Delta H value just flips sign basically here. So that's also obviously different than equilibrium where you go in the inverse of it as well. We also saw, I think at the very end, if I'm not mistaken, you could also come up with sort of a stoichiometry relationship between the energy and the reactants. So, if you did have this equation with my made up number there, let's go with 100. And you wanted to know, how much energy is needed for like, 4 moles of A. You can basically do like a mole to energy relationship, very much like a mole to mole relationship, like you do in stoichiometry. And you can say for every 2 moles of A, I get out 100 kilojoules of energy, or 100 kilojoules of energy, I get 2 moles of A. So you could just do a simple sort of energy stoichiometry problem where we would do something like this. The moles of A would cancel, and we would end up with 200 kilojoules of energy would be needed for this particular reaction. Any questions on any of that stuff? I think we talked about last time. It's been a while, but I think that's what we talked about. I did want to do one example, though, of actually calculating delta H. As I mentioned before, we'll take a look at this one here that I scribbled up here on the board. Okay, so in this reaction here, this is our reaction, and what we want to calculate is the delta H of the reaction. So as I mentioned before, in any sort of textbook in the back, there's like a thermodynamic value table where you can have delta H values, delta S values, as we'll talk about in the next chapter, delta G values. So you could go look those up. They're sometimes referred to as delta H of formation. That's what the F stands for next to those numbers. And that's where, for example, all these numbers would have came from. You would go to that table, and again, you would look up the values for everybody that's in the equation. Really important, as I mentioned, I think last time, is you want to definitely make sure when you look up the values in the table that you find not only the substance you're looking for, but you do find it in the correct state. I'll spit that out, state. So if it's a gas, you want to make sure you get the gas value. If it's a liquid, you want to make sure you grab that liquid value. The common error people make on that one is for water, because all three states are usually in that table, and people maybe just grab the first one they come across when they see H2O. So you do want to make sure that you grab it for the right states. So to calculate the delta H of the reaction, if you're asked to do that, and pretty much that's all the question gives you is like, what is the delta H of this reaction? And they just give you the reaction. You most likely will have to go look in that table to find these values. A lot of times they don't give it to you, obviously, in the problem and stuff like that. So what we would want to do is calculate the delta H of the reaction by taking the sum, basically, of all the delta H's for our products minus the delta H's for our reactants. We also want to make sure that we do take into account the coefficients in the balance equation here. So when we look up these values, they're in kilojoules per mole. And remember, our coefficients are really moles of each of these guys. So we do have to kind of multiply everybody by those values. So if we were to do this, the delta H for this reaction would be, we will start with our products. We have 16 of the CO. And again, looking up the value for CO, which is right here, we would take 16 times the value that we would find in the table for CO. We would then add it to our other product, which is our water here, which we would also take 18, which is basically the moles, times the value that we would find for liquid water in the table, which is minus 286 kilojoules per mole. And that basically takes care of all of our product side. We would then subtract it and do basically the exact same thing for our reactant side. Here we have 2 of our C8H18, which again, if we find in our table, is this number. So we would take 2 times our minus 208 kilojoules per mole. We would add it to our other reactant, which is 25 of the oxygen. And oxygen is actually 0 kilojoules per mole. Pretty much anything that is uncombined in its natural state will have a delta H value of 0, basically. So that's very common that you would see there. I don't know which one's in 17. Is this the one you have in 17? Is that what it says in 17? Did we do that last time? Yeah. Yeah, so I think we didn't do with actual numbers, right? I think we did. Yeah. Yeah, so this is an example with some numbers, but it should be very similar to what we talked about last time. Yeah, so I just want to kind of do one with the numbers and stuff so you can kind of see how it works. But yeah, it should be exactly like what we talked about before. So basically that's what we do, just kind of add all that up and see what we end up with here. So we'll take 16 times negative 110 plus 18 times negative 286. So for our kind of product side here, we get something like minus 6908 kilojoules, and that will be then minus our reactant side, which looks like 2 times negative 208 equals a minus 416 kilojoules. And that gets us, when we add those guys together, or subtract them actually, which will then add them. So we will end up with here negative 6908 plus 416. We'll end up with a negative 6492 kilojoules in this case. And that would be our delta H value for this reaction. And in this case, this reaction would be endothermic or exothermic. It should be exothermic. Again, simply the negative there tells us, which is what we would expect since this is a sort of combustion reaction. So we would kind of expect it to be exothermic. Any questions on that? So yeah, I think last time I didn't have values or tables or anything like that, but I just kind of walked you through how to do the calculation. This is again how you would do it, obviously with the numbers. Any questions on calculating delta H? Okay, then we will pick up, I think we left off at specific heat, I think, if I'm not mistaken. So let me go find that there. Everybody good? Yes. All right, so I think we talked about this, but did we do an example? I can't remember we started talking about this specific heat. So, yeah, we did talk. Okay, so we talked about this. We talked about this table, I'm assuming, yes. Did we do an example? Is that where we left off? We did two examples. Oh, so we're further than I thought. That's good. So we did this one as well? Okay, that was the last one we did, right? Perfect. All right, so obviously we talked about specific heat, which obviously, one more time, is that equation Q is equal to ms delta T. And reminder that the Q here is heat, our energy, and that is the one that has basically one unit, which is joules or calories. M is mass, which is grams. S is the specific heat capacity, which basically has 3 units, joules per gram per degree Celsius, are calories per gram per degree Celsius. And our delta T, which as we talked about last time, is really important to make sure that you do that final minus initial, because this is really where, if we end up with a negative value for Q, that's really where it's going to come from, is that change in temperature, which, by the way, I think I remember now we talked about that again. That's one of the few things in chemistry that you can leave in degrees Celsius here. Again, because usually the specific heat capacity is given to you in degrees Celsius. Q, just like delta H, if you end up with a negative for either one of those guys, that again is our exothermic process. And if you end up with a positive, obviously, for either of those guys, that's going to be endothermic. And as we will talk about, if you do sort of a very simple calorimetry problem like we're going to do next week, and you do it under constant pressure, you are kind of correctly calculating delta H. And it's a very simple experiment to do. Just need a thermometer basically and some water, and you could kind of do this type of experiment, and you could calculate the delta H for a reaction very, very simply by actually just using a couple of coffee cups. Now, when we talked about heat being transferred, as we talked about, heat does transfer from basically the hotter object to the colder object. And sometimes we get that transfer, for example, is if we have, for example, some water, and let's just say our water is at like 25 degrees Celsius to begin with, and we take like a piece of metal where we know the mass of the metal, we know the initial temperature of the metal. We can then, if we take this metal and kind of heat it up, and if we take this guy to a temperature, say like 99 degrees, which is obviously much hotter than our water there. And if I take this piece of metal and I throw it into my water, what is going to happen in terms of the metal is obviously it is going to release energy, right? It's kind of exothermic in terms of the metal. The water is basically going to gain all that energy. So it's endothermic for the water that is sitting there. Eventually, what will happen to this piece of metal is it will come to rest at a final temperature. We'll just call it 30 degrees Celsius. And the water temperature will rise, obviously. The metal's temperature will basically start to decrease. The metal should end up at what temperature? The metal will end up here at the same temperature as our water, right? Because it's sitting in there. So eventually they will come to equilibrate to the same temperature. So by doing a simple process like this, we also will know the final temperature of our metal, which would be 30 degrees since it's sitting in that water. And since we can assume that all the heat that was transferred to that water would come from the metal, we can use really the water to figure out how much heat was absorbed by the water, which would also tell us basically how much heat was lost by the metal. So if we just think about sort of the water part of this thing, we have the mass of the water, we have the initial temperature of the water, we have the final temperature of the water, and we always have the specific heat capacity of the water, which, by the way, is that 4.184 number that we saw on that chart. And from that, we could actually calculate the Q of the water by using all of our values in that case. The relationship is there's a opposite relationship in terms of the sign of Q between the metal and the water. So Q of the metal will equal minus Q of the water, which means if I end up with a positive number for my water, which I should for Q, the energy that was released by the metal would be the exact same number, except that it would be negative and exothermic in this case. And if I do this, I can figure out something about the metal. So perhaps maybe I was looking for the specific heat capacity of the metal. So by using the water, I could figure out how much energy the metal lost. I would obviously know the mass of the metal. I will also know the change in temperature of the metal. So I could rearrange this and solve for the specific heat capacity of the metal. So this is a very common sort of experiment that is done. You could do it in parts. You could set each of those things equal to each other. So that's what this equation is. We assume zero heat loss. So basically, you just got to change the sign on one of them, basically, and it'll work out. But it's sometimes easier just to do it sort of separately. So next week, I think when we throw some pennies into water, which I think is what we're going to be doing, you can heat up some pennies, drop it in some water, and pretty much do this type of experiment here. You can figure out like the specific heat capacity of a metal by really following the temperature change in the water. That sort of process is sometimes referred to as calorimetry. And again, you can do it with just simply 2 styrofoam coffee cups and a lid. Works really well. Keeps any heat from being lost to the surroundings. So why don't you try that one, an example like that. Let's say we had a 110-gram sample of a metal that's at 55 degrees Celsius. It raises the temperature of 150 milliliters of water from 23 to 25.5. Determine the specific heat capacity of the metal. So why don't you give that a go? Okay, let's take a look. So this is very similar to what we were just talking about. So we basically got some water. We're going to take a piece of metal that we heat up and basically drop it into our water here. So we do have 2 things. So we have some metal information over here. So for our metal, we obviously have the mass of it, which is 110 grams. We have the initial temperature there of the metal, which is 55.5 degrees Celsius. It raises 150 milliliters of water. So we got some information about water over here. By the way, 150 milliliters of water, if we use the density of water, which is typically 1 gram per milliliter, that would tell us that we have basically 150 grams of water, which would be the mass. So again, remember, you can always use obviously the density of water there to get to mass. We have the initial temperature of our water, which was 23 degrees Celsius. Our final temperature of our water there ended up being 25.5 degrees Celsius. And remember, we always have the specific heat of water, which is 4.184 joules per gram per degree Celsius. As we talked about a second ago, when that piece of metal goes into the water there for a swim, it will also eventually end up at the exact same final temperature as the water. And that would also be our final temperature here of our metal, which would be in this case 25.5 degrees Celsius. And we are looking for the specific heat capacity here of our metal. Any questions on that so far? So again, just looking at it, we pretty much have all the information that we need for the water. So we might as well just go into the specific heat equation for the water, which would be the MS delta T here. Putting in our number, we got 150 grams times the specific heat of water times our final temperature, which is 25.5, minus our initial, which is 23, degrees Celsius. And if we do that there, and don't hit extra numbers, there we go. We do end up with something like 1,569 joules. If you really want to do sig figs, that would be 2 sig figs off of this guy, which means this probably should be somewhere in the neighborhood of 1,600 joules, as that's 4 sig figs and 4 sig figs. Again, when you subtract that, you get 2.5, which would be 2 significant figures moving across. Any questions on that so far? Now, that is how much water, that is how much energy that the water absorbed, right? And it is a positive number, which makes sense, right? It is endothermic, so it's picking up all that energy. The assumption here is obviously 100% of the energy that the water picked up came from the metal that was dropped in there. So that is where we could use that relationship. Basically, Q of the metal is equal to minus Q of water. That means our Q of our metal here would basically be the exact same number, and I'll use the rounded one, why not? Minus 1,600 joules here, except that it will be negative because for the metal, it is exothermic, so it should be releasing that energy as you go through it. Any questions on that there? That's significant because really that was the last piece of information that we needed to be able to calculate the specific heat capacity of the metal. Because now if we look at our equation for the metal, we have ms delta T. We obviously have that, and we have that. So we can solve for S, which would be Q of the metal divided by m delta T. Putting in our number, minus 1,600 joules divided by our mass of the metal, which is 110 grams, divided by our final temperature, which is important here because it is 25.5, minus our initial temperature, which is 55.5 degrees Celsius. That is important because that difference there will now give us a negative value, right? And the negative value on the top will turn our specific heat capacity into a positive number, which is what it should be. So if we do all that good math there, we end up with 1,600 divided by 110 and divided by basically a difference there of 30. Gives us a specific heat capacity of 0.48. None of these units cancel, which is good because specific heat capacity should have all 3 of those units there, which would be 0.48 joules per gram per degree Celsius. Any questions? That would be the right sig figs, I believe, because when you subtract here, you get 30.0 basically on the bottom, which would be 3, this would be 4, and this guy would still have 2. So 2 sig figs. No, because on my calculator, I got like 0.484848. So since we needed 2, we would go to the 8 and look at the next number, which would be 4. Yeah. It is because the water here from our calculation gained positive 1,600 joules. And again, that's because the water, it's endothermic, is picking up all that energy. All that energy had to come from the metal, which would be exothermic. So it should be a negative value, the exact same amount of energy, just negative because it is exothermic. And it's important because here we see that because the metal is exothermic, what we see when this temperature is it actually decreases, right? As it loses that energy, the reflection of that is the temperature goes down, and that gives us a final temperature that's less than the initial, and that obviously gives us a negative on that side. So those 2 guys cancel each other out, the negatives. Other questions? Yeah. It's just sort of a known value, like in that table we saw on a couple of slides back. You can find it there. It's a good number to know, especially for specific heat capacity for liquid water. That comes up a lot, the 4.184 joules per gram per degree Celsius. Or if you're doing calories, it's 1 calorie per gram per degree Celsius. But that's for liquid water. And I think we also talked about it last time as well. When you go to like a specific heat capacity table, you also want to make sure that you not only find the substance, but you find it in the correct state. So I think we saw ice, for example, which is water, is like a value of 2 joules per gram per degree Celsius. So there are different depending on the stage. So you want to make sure that you find it. But very common, we use water to do these type of experiments. And in most cases, if you make a solution, like you take an acid and base and put them together, those are aqueous solutions, which in the most part is basically water-based. So we oftentimes will, even in a reaction sort of situation, if you do this like in a calorimetry type cup and it's like an acid and base, we would still use like the specific heat of water because the majority of it is basically a water-based solution a lot of times. So even on something like acid or something like that, you might still use 4.184. Other questions? All right, questions on specific heat. So obviously you need to know how to calculate it. Like I said, I think we're doing a lab next week on specific heat. So let's talk a little bit about energy and nutrition. I think we might have talked a little bit about it the other day as well. There is sort of another calorie, which is more of a nutritional calorie, and that's a calorie with a capital C. One of the nutritional calories is equal to 1 kilocalorie, which is basically 1,000 of the little calories in there. So typically we use nutritional calories always for food. That's how they calculate. We'll talk about here in just a second, like all the stuff on the nutrition label, you know, how many calories there are in a candy bar or something like that. A calorimeter is a apparatus, and again, it can be as simple as 2 coffee cups, which we'll use kind of next time, but it can be a really nice equipment as well. This is what is sometimes referred to as like a bomb calorimeter because they basically ignite it on fire. So you put like your food sample or your cookie, I suppose, you got some wire in there, and you have oxygen-filled container. That's a pretty much isolated container there. It's not going to lose any heat or anything to the environment. And basically set that piece of food on fire. As the food is burning, it's going to transfer the heat and energy to the water. And by just simply monitoring the temperature change there and using like the specific heat equation, you could calculate how much heat is lost by the piece of food. And you could obviously figure out how many calories that is as well. At school, I used to teach that. We used to do a cheaper version of that where you take like a Coke can and fill it up with some water, take like a Cheeto underneath it, set it on fire. And the heat from the Cheeto or the peanut they sometimes used would heat up obviously the water in the Coke can. And again, simply just following the change in the temperature of the water, you could do some calculations, very simple calculations like our specific heat calculation, and figure out how much calories are basically being given off by that food sample. Now, food does have a caloric value, and the 3 types of sort of values are carbohydrates, fats, and proteins. And each of these do have a value that you could use to calculate how many calories there are. For carbohydrates and protein, it is 4 kilocalories per gram, basically 4 nutritional calories per gram. And for fat, it is 9 kilocalories per gram, or again, 9 nutritional calories per gram. If you look on most food labels, they will tell you, you know, carbs, how many total grams there are, protein, you know, how many total grams, and obviously fat, how many total grams. And you could do this sort of calculation, and that technically is sort of how they are supposed to calculate the calories per serving per se that you see up there on your nutritional label. And again, you just simply take the grams times the caloric value, and at the end, you just add them all together, and that would give you obviously your calories. In most cases, they do round a lot. They round down a lot of times on those calculations, oddly. Another way that we do really in the lab, and again, this is sort of what we will do in the experiment, you can make a very simple calorimeter by just using coffee cups, styrofoam cups. They insulate really well with a lid on it, with a hole for your thermometer where you could put it through. And you just kind of stack them together, make some good insulation. And you basically just run your reaction inside the cup. So you can do like an acid base reaction, put it together and let it do its thing. Like I said, you can take some water and heat up a piece of metal and put it in there and kind of do it. And basically you could just follow the change in the temperature there. And again, simply use our specific heat equation here to calculate the heat that's either released or absorbed by the reaction. And if you do this at constant pressure, when you actually calculate Q in this situation, you are calculating basically the delta H for that reaction under constant pressure, which is in most cases. So a very simple experiment, you could directly calculate the delta H of a reaction. And if you know, like, for example, how many grams you started with of something, you could then do, how many joules or kilojoules per mole by converting, obviously, the grams you started with into moles and kind of dividing it out. So you could actually do a very simple sort of experiment and actually calculate the delta H for a reaction. As long as you keep the pressure constant, which is usually the case, it doesn't really change all that much. So for example, here, if we had a serving oat bran hot cereal and a half cup of milk, contains 22 grams of carbohydrates. So if we want to know how many calories that would be, you would take your 22 grams of carbs, and you basically would times it by the caloric value, which is 4 kilocalories per gram. That would get you something like 88 kilocalories for the carbohydrates. You would take your 7 grams of fat and times it by the caloric value for fat, which is 9 kilocalories per gram. Again, the grams cancel. And I'm going to use my calculator here. It's late. 63. That sounds good. Surprise math. 63 kilocalories there. And 10 grams of protein, which also has a caloric value of 4 kilocalories per gram. Again, those will cancel. I'll do 40 there, kilocalories. Now, if we add all that together, 88 plus 63 plus 40 gives you about 191 kilocalories or nutritional calories. But that is per serving. But here we did eat 2 servings because we were hungry. So we should probably times that by 2. And that would be something like we ate 382 calories at our breakfast. It's a good way to start the breakfast in the morning there. So that's, again, a way you can do that. And like I said, if you take any nutritional label you have for food and you can do that calculation, again, that's technically where, the calories come from on those nutritional labels. Like I said, a lot of times they do round down. A lot of times they don't really follow strict rounding rules there, rather than let's just round it down. Any questions on how to calculate that? So the last thing that we're going to, I think, talk about in this chapter in terms of energy is we talked about delta H and how to calculate it, a couple different ways of using delta H. Obviously, you could calculate it like we did here at the opening today and did products minus reactants by looking up the values. You also can use delta H like we did the other day, sort of manipulating the equation. And, an equation that has a delta H value with it, either multiplying by a number, dividing, or use it as sort of a stoichiometry conversion. Another important aspect of sort of delta H is the idea of Hess's law. Hess's law basically states that an equation for a reaction is basically the sum of 2 or more other reactions. So the idea behind Hess's law is the idea that, if I have a reaction like A plus B goes to E plus F, a lot of times people think that this reaction might occur in a one-step sort of process. And it doesn't always occur in one-step process because energy and enthalpy is a state function, as we talked about. Really, the only thing that's important is sort of where you begin and where you end. And it doesn't matter if you remember the picture of the hiker going up the mountains, right? You had one that kind of went straight up, right? One took sort of the scenic route around. In terms of their potential energy, they were both the same because of where they started and where they ended. So the same thing happens with reactions. You could do it in sort of one reaction if it's possible. It may take several individual reactions, 2, 3, 4 reactions, sort of all added together to get you to where you want. So for example, maybe this reaction occurs, A plus B makes C plus D. Maybe there's a delta H value there associated with it. And then maybe the next thing that happens is C plus D makes E plus F, where there's a delta H sort of associated with that. If you take this reaction and add it together, Much like all of the times we've added reactions, anything on opposite sides of the arrow that are the same can either cancel or reduce down. So C and C would cancel, D and D would cancel, and that would get you A plus B gives me E plus F, which is sort of the goal reaction of what I'm looking for. So if I wanted the delta H for this reaction, I would simply just add up my delta H values here. So I could just simply add those together, and that would give us the overall reaction that's happened here. Now, in this process of doing Hess's law, which is essentially this idea of they give you sort of a overall reaction that you're looking for, and you need to take a bunch of individual reactions basically to build the reaction you're looking for. This is where we talked about earlier that you may have to manipulate some of these equations. You may have to reverse a reaction. So a reminder that if you reverse a reaction that has a delta H value, the delta H value changes sign. So if it's positive, it becomes negative. If it's negative, it becomes positive. The number doesn't change. If you need to multiply by the reaction by a common number, as we talked about earlier today, you basically wouldn't multiply the delta H value by that common number. And again, if you need to divide by a common number, you would divide the delta H value by that common number. So in Hess's law problems, sometimes you do have to sort of manipulate the different equations, move them around. And the easiest way to sort of approach Hess's law problems is simply just like get everybody on the right side, basically. You know, start with one thing in the reactants that you're looking for, find that in the individual equations. If you need to move it around or to the other side, get everybody to the right side with the right amount, and that's usually a good approach to doing these type of problems. And as I wrote over this here, so we can take a look at this. So again here, if we were to take these two reactions and add them together, the water and the gas phase would cancel. And again, we would just get this by summing these two guys basically together for this overall reaction, which would be our formation of water, which we saw earlier was like 286 kilojoules minus 286 kilojoules. All right, so if we look at this reaction here, our desired equation is the guy on top, and we're really looking for the delta H value for this. So again here, what we would want to do is just kind of keep everybody on the correct sides and see what we need to do. So if we look here, we do have a carbon, and this is the only reaction that has a carbon, and they're actually on the correct side in this particular case, so that's not too bad. So I would probably just recopy this guy exactly the way it is. Since we really didn't do anything to this equation, the delta H will remain the same. Nothing will change. The next thing that we might want to look at is the CO2, which is on the right-hand side. And I do see CO2 on the right-hand side. And I do need one of each of those, which means in this case, this is a pretty straightforward example. I actually don't have to do anything to this guy either in this case. And if I did that right, since there's no other equations left, if we add these together, the CO should cancel. And that would leave us with a carbon plus half and half gives me one oxygen on the left. Plus goes to my CO2 on the right. And again, my delta H in this case would be simply adding these two guys together, which in this case would give us 110 plus 283, it looks like. Gives us a negative 393 kilojoules. This reaction would be endothermic or exothermic? Exothermic. And again, in this situation, I actually didn't have to do anything to any of these equations. Not always the case. You may have to obviously flip them around, multiply by a common number. But that's sort of the idea is you sort of have an equation you're looking for, and you just got to kind of build it from the other equations. And the key is to really kind of like what we did with the K values is to keep track of what you did to each one and make sure you adjust the delta H's correctly. Question? Yeah. That is, I think the C you're talking, or the CO is, it is a G. It's just a tired G. There you go. Yeah, no, it should be a G. It's a G here and a G here. The only solid, I think, is just the carbon. It should be that guy. Other questions on that? All right, let's try another one here, I think. Yes. So why don't you give this one a go and see what you come up with? I suppose the right answer is there somewhere. Yes. So we're looking for the delta H of the top one using the other two pieces of information. To look, so again, personally, I just start with the equation I'm looking for. So I have SO2, which clearly I see in this equation. First thing I notice, it's on the wrong side. I do need one SO2, and there is one SO2 in there, but again, on the wrong side. So I do need to reverse that first equation. So that's basically what I would do. I would take the SO2 and take the S plus the O2. Because I reverse this equation, what's going to happen is the sign of it will change, and it will go from negative 297 to positive 297 kilojoules. So that takes care of that. The next, maybe I'll look at the SO3, which does need to be on the right-hand side, which it is. But again, here in the final, I just need one of them. So I do need to come through here and divide everybody by 2. And if I do that, I will end up with an S plus basically 3 halves O2 gives us a SO3. Because I divided everybody by 2, I will also divide my delta H by 2 here. And that gives me a delta H, which will remain the same sign because I didn't flip it, but it will become 792 divided by 2 minus 396 there, kilojoules. Now, if I did this correctly and I add these two together, I should end up with the equation I'm looking for. So it looks like S cancels. I have 1 O2 and 3 halves O2. That's 1.5 minus 1 leaves me a half O2 on this side. Right. So that leaves me basically my right equation, SO2 plus 1/2 O2 on the left gives me SO3. So that is exactly what I'm looking for. Again, 1 minus 3 halves gives you just a half that's left over. And if I do that, then I just need to add my values here. And if I do that, 297 minus a 396 looks like a minus 99 kilojoules would be our overall value here. Any questions on that there? So Hess's law is really just that. Just you just want to kind of keep track of everything, move things around. And really, a lot of times just kind of going left to right there, getting everybody on the right side. Everything else should sort of fall into place, all the other stuff along the way. Any questions on Hess's law here? Yes, sir. You can. So it doesn't have to completely cancel out if that's your question. You could kind of think of like in this situation when you're adding equations together, like the arrows, like an equal sign. So like just a math, like if you had like 2x on one side and x on the other side, and you brought it over, you would be left with just like an x on one side. So it kind of works the same way. A lot of times it'll kind of completely cancel, but they don't have to completely cancel. You could just reduce it down. Because you never should end up with, in most reactions, you never should end up with the exact same thing on both sides, right? Because the idea of a chemical reaction is everybody sort of changes partners, becomes new things on the other side. So if you brought both of those things down, you shouldn't technically have an O2 on both sides. That's why you should kind of combine them to one side and reduce it down. Other questions? Okay, so I think what I like to do is just, talk to you. No, I'm just kidding. Now, I'd like to talk about one little thing about specific heat and tie it into a couple of energy values that maybe you learned about in Chem 200, since we got just a couple minutes here left to sort of talk about it. Now, we talked about specific heat, which is really used for when we basically change the temperature of a substance, but really we keep the substance in the same phase. There is energy related to, again, just changing the phases of things. And if we look at sort of a heating cooling curve, for something like water, and this is like 0 degrees Celsius, Imagine that's a straight line, and that's 100 degrees Celsius. So this would be like ice. This would be like liquid water. This would be like steam, which is the gas version, right, of water. So basically gas, liquid, and solid, right? Now, phase changes, right, between, say, solid and liquid happens at the same temperature, right? The only difference is whether or not you are continue to supply energy in, right, or take energy out. So the melting point and freezing point of water is actually 0 degrees. At exactly 0 degrees, it is plateaued-ish, straight line. And basically exactly at 0 degrees, for example, for water, you have like ice crystals there. So you got some ice and you got some liquid water. Not until you get above 0 degrees Celsius, right, that you get truly liquid water, not below 0 degrees that you actually get ice. But dead on there at 0 degrees, that is where the phase change occurs between solid to liquid. And there is a certain amount of heat required to do that change. And that is what is referred to as the delta H of fusion, or the heat of fusion. And for water, for example, and this is just liquid water, it is, or just water itself, I'm sorry, it's something like 333 joules per gram, or roughly 6.02 kilojoules per mole in terms of the heat of fusion. It is the energy required to do nothing more than to take water in the solid phase at 0 degrees to water in the liquid phase at 0 degrees. Temperature doesn't change. So when we change something in terms of phases, temperature stays the same, but the substance changes phases. We use something like the heat of fusion for the solid to liquid or the liquid to solid. It doesn't matter which way you go, the number is the same. And again, this is specifically for water. The only difference is the sign. As I go from solid to liquid, is that exothermic or endothermic? Solid to liquid is endothermic. So that would be positive 333 joules per gram. Going from liquid to solid, that is exothermic, and it would be minus 333 joules per gram. Same thing happens up here at 100 degrees Celsius. That is the normal boiling point for water. And again, at 100 degrees Celsius, you have both phases in equilibrium with each other. Not until you get a little bit above 100 degrees, you got steam. Not until a little bit below 100 that you still have liquid water. And there is energy required, again, to do nothing more than change the phase, not the temperature. And that is what is known as a delta H of vaporization. And for water, it is roughly 2260 joules per gram, or we'll go with 40.6 kilojoules per mole. And it's the same idea at 100 degrees, going from liquid to gas or backwards. It is endothermic, going from liquid to gas, and that is a positive 2260 joules per gram. And it is a negative exothermic process going the other way, minus 2260 joules per gram. When you look at a heating and cooling curve, anywhere where it plateaus, and again, imagine that's a straight line, is basically a change of phase, but not temperature. And when you do anything like that, change the phase, not the temperature, you should be using heat of vaporization, heat of fusion, maybe heat of sublimation. Those are the guys that you should be using. Anywhere like we've been talking about where you are kind of going upwards on this graph, everywhere it is green and we're going upward on the graph, that is all situations, for example, all liquid throughout that green part there. And we're changing the temperature. So the substance stays the same phase, but changes temperature. That is where you use specific heat capacity equation on those steps. So for example, if we wanted to figure out the heat or energy to take 105 grams of ice at 0 degrees Celsius to 105 grams of steam, if I could write steam, at 100 degrees Celsius, we could use a combination of all these things to get us there. So let me redraw our little graph here. So if we were going to take 105 grams of ice at 0 degrees Celsius to basically 100 degrees Celsius. We would be starting right there. And the very first thing that we would have to do is actually take the ice from 0 degrees Celsius to liquid water at 0 degrees Celsius. That would be really the first step that would happen. And that means that we would go from 0 degrees Celsius ice to 0 degrees Celsius liquid water. And that would be our heat of fusion that we would want to use. So to calculate the energy required to do that, this would be positive endothermic. We would use the heat of fusion for water, and we would use the mass, so 105 grams, times my 333 joules per gram, which is the heat of fusion for water, would give me, for that step of the process, 105 times 333, roughly 34965 joules. I am now sitting, after I do that transition, I am now sitting right here. The next thing that would happen is that liquid water at 0 degrees would go from liquid water at 0 degrees to liquid water at 100 degrees. That is liquid water all the way through that process, stays the same phase, but we change the temperature. So for the second part of that process, we would actually use the specific heat equation to take it from 0 degrees liquid water to 100 degrees liquid water. And that would be, our mass would be the same mass, as long as we didn't drop it. We would use the specific heat capacity for liquid water. Our final temperature would be 100 minus our initial temperature, which would be 0 in this case. And we would have 105 times 4.184 times 100-ish. Guess me, looks like, I believe, hard to read this calculator, but I think it's 43,932 joules to do that transition. I'm close to where I want to end, right? I do want to end at 100 degrees steam, but right now I am sitting at 100 degrees liquid water. So the last thing that it has to do is one more little phase change, which would take me from 100 degrees liquid water to 100 degrees steam at that point. And that would be the heat of vaporization that's necessary to do that. Again, you would use the value for water, which again is roughly 2260 joules per gram. And that gets you 105 times 2260, around 237,300 joules. I am now where I want to be, right? So to figure out the total amount of energy to do that whole thing, right? I do what? I add up all those numbers, right? So I do the total energy would be step 1 plus step 2 plus step 3. So I won't rewrite those numbers. So for our purposes here, we end up with 43,932 plus, where was our first step there? 34,965. Roughly 316,197 joules, or if we want kilojoules, about 316 kilojoules of energy is needed to do that entire process, to take it from the different phases. Any questions on how those things relate to each other? By the way, does it take more energy to go from liquid to gas or solid to liquid? It does take more energy to do liquid to gas, as you can see here, right? About 237,000 versus like 34,000 to do the other one, right? That is because as you go from solid to liquid, everybody's still relatively close to one another. But when you go from liquid to gas, everybody is completely broken apart. It takes a lot more energy to do that. Last question would be, if I started with the steam at 100 degrees Celsius and wanted to finish at ice at 0 degrees Celsius, what would change here? Yeah, basically the sign would be different, right? The first guy would be negative 333, which would give you a negative number. Second guy would be 0 to 100, which would give you a negative number. Third guy would be negative 2260. You would end up with the exact same number, except that the sign would be negative because it's exothermic going in the opposite direction. Any questions on energy, chapter 7? Okay, we were laid up there, and we